built an implementation. It's out there. People can use it. People are already hosting websites on it. And it's all moving really fast, and it's exciting. And we try to keep up with the usage and feature requests and all that kind of stuff. And so yeah, if you want to get involved with the process, we have a very open community. We have a lot of people from very different backgrounds coming together. We run the show in a best idea rules, and our focus is on making the internet better, as you'll hear in a second. And yeah, we welcome any contribution from anybody, and we're just interested in making better tools and picking the right path forward for making the web better. So with that, I'll just give so a lot of you already know IPFS, but I'll just give like a super quick introduction as to why IPFS matters in a sort of general context beyond sort of distributed projects or distributed systems or cryptocurrency space or file replication. This wasn't actually apparent to me until much later. The ideas behind IPFS have been around for a long time, just not put together like this. And it became, I got to understand why the web is broken right now, and why it needs some help. So this is the Wi-Fi stuff if you need it. Everyone got it? Good? The internet is this huge nervous system, right? And I say this a lot, but it's true. We're constructing this massive, we already did construct this massive piece of technology that we're all part of, and we run our lives through it more and more. I go through weeks now where I don't really realize where I am, because so much of my life now takes place through the tubes, through the network, right? Most of my relationships I upkeep through the computer. Most of my conversations are most meaningful when put in writing, which oftentimes, not all conversations, but most conversations get to the core of the ideas through writing, and most of that happens through email. And 3 decades ago, the web wasn't around. And in a very quick span of time, we are now all part of it. And we run our lives through these kinds of applications. Not only do they have all of our files and all of our documents and all of our life is now running through this network, but we learn how to be a human through this network. Our capabilities are defined by the applications that we use. So whenever you want to give so the cool part of this is that if you want to give humanity a new capability, a new way of doing things, something that humans couldn't do before, and you can do it in software, or some amount of hardware coupled with software, you can push it out to the rest of the world very cheaply and very efficiently. That's incredibly powerful, and we all know this, but it's important to remember it because it's been hurting recently. And what I'll do really quickly is I'll go through some of these problems. I'll give you like a tiny little overview on the data structure of IPFS, and then we'll get to a demo. But the problem of the web is that it began, this is Paul Baran or Baran, I forgot how to pronounce his name. He's one of the people who came up with packet switching. And at the very beginning, he gave this characterization for networks, and they're either centralized, decentralized, or distributed. And this picture is great because the web sort of started over here, right? And in the very beginning, when Tim was constructing HTTP, he had this vision of people running HTTP servers and people running HTTP clients, and you would use both a client and server to fetch files from each other and exchange. And this amazing explosion of power that came along with the ability to publish documents that anybody else in the world could read at a permanent URL, at a permanent location that you could hand out was tremendous. And his vision began that way, and a lot of people started running HTTP servers and clients and so on, but very quickly over time, it started to centralize. And today, when you think about it, stop for a moment. A lot of people in this group will be thinking about the future and things that we're building now and like how things are going to be 5 years from now. But think about how your life is today. Think about how many things are centralized and how many of your services are all pointing to one specific location. And this isn't about organizations or companies having control, although that is, of course, an important piece of the puzzle. Like the fact that a small set of organizations control the majority of the web presence of your life, which means that they actually control all of the stuff that you produce. in a weird way. And of course, because everything is going well, and the good graces of all the web services point to things staying this way, it is not a given. But not really going to talk about politics. What I'm going to talk about is the fact that all of the content points to some specific set of places on the web, right? So a URL is like the ills that come from location addressing. When a URL which has a domain mapping to an IP address, which specifies a specific set of computers that are going to serve this. And people, of course, hack around this by creating clusters that are represented by a virtual host that is at one location, pseudo-location. This is clearly like just patchwork. Most people never use those capabilities of the web, and most people are stuck in a world where all of their objects have to point to some centralized organization and to some centralized location. Didn't have to be this way. It was actually the easiest thing to do back then, but these ideas around how to do it differently were around before. So to illustrate this, if all these people have a file that you're interested in, and only that computer is at the address, so only that computer can serve it, no matter where it is in the network, who controls it, who owns it, what rules or laws it behaves under. So there's a ton of problems from this, right? Like bandwidth latency are the most obvious ones. You don't really want to go around the world to fetch stuff, particularly if it's right next to you here. But it also does some other things, like it creates this concept of being online and offline, or at least even though we have computer networks everywhere in the planet now, we still have to deal with the fact that there's an online and an offline world, and that when you're online you can access your data, and when you're offline you can't. And of course some applications try and deal with this by doing their own sort of proprietary protocols to move data around and so on. What we're really struggling with is the fact that the web cannot express the notion of looking at content as content itself and separating it from the notion of where it's stored. I should be able to write a website that points to content, and that content should be able to be served by computers next to you without having to go and fetch it from the rest of the internet, so that it continues to function if you, for whatever reason, get disconnected from the backbone. There's security to deal with. Of course, if things were different than they are today, we're going to have many different kinds of security challenges. But today, when we store documents on the web at a specific location, we are putting all of our trust in Notion. We're entrusting all these other organizations with our data and giving them sovereignty over it. And we're not used to encrypting data. We're used to encrypting the wire between us and the organization. But that's not good enough. Like, why do we have to store stuff on Dropbox unencrypted? Why can't we encrypt it at rest? There's a lot of reasons, perhaps, but maybe they're not as valid as we might think. I want to move the world towards a cloud that takes security very seriously, and where a person that wants to store encrypted data can. And today, that's not easy. That's actually not, like, you have to be a security expert to do it right. I talked to the Tarsnap guys. Like, they work hard to do this. Permanence is important. I'll talk about it in a second. Multiple devices, think about how many computers you have here, and when your data is stored in one computer but not the other, and you want to use some file, and like you have to pipe it through the backbone, because why? Because we have URLs structured in terms of location. Right? So yeah, bandwidth and latency. Big room like this. I upload a picture, give you a link, and now you all have to go fetch the picture, right? It looks like this in the backbone. So send a picture up, and now everybody requests it, and everybody pulls it down. So 240 megabytes for like a 1 megabyte picture. That looks a lot worse when you have video, right? So that's potentially 48 gigabytes. In a room full of 30 people, it's 48 gigabytes through the pipes. It seems like a big waste to me. This online-offline thing, imagine if you open a Google Doc with somebody else and you start working, and everybody else in the same room starts working, and why are you piping everything through the backbone, right? Or what if the pipe is very small, like in a third world country? We don't suffer this as much here in Silicon Valley, or maybe I should say in places like Estonia or South Korea. We definitely suffer it here. And maybe in third world countries, it's almost impossible to work this way. Imagine a school that wants to give kids access to the network and wants to give kids access to the web, and they're stuck through very slow pipes where this becomes impossible. And what happens if the pipe breaks? Suddenly, your collaboration, your entire application comes crashing down. This is, in my point of view, at this point, it was acceptable for a long time. I think we're reaching the point where this is no longer acceptable. And we as engineers, in all our different capacities, whether it's as engineers of applications or engineers of infrastructure, have to make the conscious effort to move away from these models to a model where personal computing, and by the way, and on this, big thanks to Cal Drake, who made me think about personal computing as the crux of the matter here, where you are computing on your information, and you should be able to compute it with other people and your peers next to you, not through computers in the backbone. Unfortunately, I tried all of these applications, and all of them didn't have a really good model for doing offline. Even Wikipedia, which is, you have to go to lengths to make it work, where you download local caches and that kind of stuff. Dropbox is probably the best. And this is kind of really sad when you think about how important these applications are to people's daily lives. Or, when your government decides to surprise you with oppression one morning, like, what do you do when they cut off the pipes to the backbone and suddenly your entire communication infrastructure, the amazing, beautiful, wonderful tools that you have to communicate with all your friends and all your family and all of your coworkers and all the people that you trust are now off, right? So people thankfully sprang to action and built mesh networks to make this work. I think this went out.
Just give it a second.
All right. Thankfully, people sprang into action, and many people in Egypt are extremely lucky that there were a bunch of hackers there who said, "Great, let's build mesh networks right away and connect to some other pipe." But that's not easy, and it's not a given that it will work always, and it puts a lot of people at risk. When in reality, applications should be able to work in these kinds of disconnected environments. And we have the technology, right? Like, this isn't like rocket science. Like, we know how to do this stuff. We've had operational transforms for a long time. We now have CRDTs as of recently. These are convergent data structures that allow you to write applications anywhere, so that it's eventually consistent across the entire internet, which is really cool. Permanence is really important to me. Over time, we've vilified the notion of burning books and said, like, societies are only societies that go through the lengths of burning information and burning ideas are some of the worst societies in history. And we say this is really wrong and really inhumane to the future. And that's a symbol of oppression. So the crazy thing, though, is that it's getting worse, because back in the day, when you had a printing press, you could create a lot of books very quickly, and if book burners came by, they could destroy a lot of copies, but you had more and you could copy them, right? And this was just a process, and it was slow. But we're getting to a point in the web where the content may be replicated, but the link's not there, and the reference is not there. So for all intents and purposes, the thing isn't there. Applications aren't going to go and do a search on content. Like, that gets extremely complicated to go and do a search on content to try and pull it down and make you compute on it. Of course, in some cases, this is exactly what happens, because it has to, because they know that URLs will break. But it doesn't have to be this way. We could create content that is permanently addressable forever, or for some conception of forever that isn't dependent on the location of the content. So links break. And so this web of documents that we had is really a web of documents on devices. And if you go and destroy one device, or take control of it, or co-opt it, or whatever, those documents are no longer there, even if the same thing exists elsewhere. So that's those are some of the problems that IPFS is here to solve. And it's become clear over the last few months that our task is, we have many tasks that we're going to do, but a crucial one is upgrading how the web works. In relation to how we might build new internet protocols to make the web better. So this isn't a notion of let's patch HTTP, because I don't think that's feasible. I think we need some redesign of how we structure our data. All right, so hopefully we can make it more distributed, right? And so IPFS does away with the notion of client and server models. You can use IPFS as a client, you can use IPFS as a server, but the code is the same, the protocol is the same, and any single peer can compute and move around data and reference data as a peer in this huge network. So content addressing, the magic sauce, and there's a lot of interesting stuff in here, and I'm sure that all of you already know content addressing to some extent, but if you don't, the point is that instead of this old model of addressing by location, let's address by content. Let's use the content itself to describe the address of the content, or the reference that we have, or that we hold to the content, so that we can hand out references to this content, and other people can resolve them, and fetch the content from wherever it makes sense to fetch it. That might be over the whole backbone, or it may not. It may be local. So in the content addressed world, it looks like this. Instead of HTTP this way, we would have any computer in the network that has that piece of content can serve it to you, especially if it's next to you. There's of course a bunch of security problems here to think about, because you may not want to be fetching everything from your neighbor. Your neighbor might be interested in making lists of people that look at bad content, for some definition of bad, where bad could be an important document that in the Egyptian revolution that told people how to organize. So you may not want to be fetching it from everybody around you, but these are solvable problems. It's not that you only must do the TLS thing to the rest of the internet. So we move from the old model to this, where we only really download the file once, we can share it, and if the pipes go down, we can still use it. And the important thing here, by the way, is that links don't change, right? The links stay the same, and the references stay the same. So the URLs and the applications and all the JavaScript that you're running in the browser should still work. All right, so I hope I've impressed upon you what are the problems, how we might go about solving at least some of them, this is what IPFS is, and it's a way to make the web better. We combine a whole bunch of other technologies in here. You will see that there is no cryptocurrency in there. It's because it comes on the side. Cryptocurrency, for all you people that are here from Ethereum, cryptocurrency becomes relevant as a way to store content and make it persist, and incentivize computers to stay online, and incentivize human maintainers of computers to maintain those computers and keep them online. But it's not core to IPFS, so we put it into a separate protocol that we call Filecoin, and there's some other interesting stuff there. IPFS translates to a stack like this. I'm sure this is not really that important to you, but the important thing here is that it layers. And so an IPFS node will include all these pieces, but it's layered so that we can evolve it should we need to. So that if the routing systems of today, which perhaps are at DHT, if we come up with some better way to do routing, we can swap it in without having to change the architecture of the web or all the applications that depend on that.
You should quickly say what SFS is.
Oh, sure. SFS is one of my favorite pieces of technology. So I feel like a hipster knowing about SFS. So SFS, David Maziris, who is, I guess, most recently known to the cryptocurrency community through Stellar, and before that he made Kademlia, which is probably the most widely deployed DHT ever. Was actually my distributed systems prof, and some earlier today. He invented SFS as his PhD thesis, and the idea was very simple. He was very frustrated by the fact that the CA system imposed this notion of having a huge CA organization that signed records and so on, and you could derive random organizations that don't really relate to your notion of trust that can then still sign certificates. And he wanted to move away from a world where you had to ask somebody for a certificate, where you had to ask for the ability to sign a name or sign a record. And he said, well, of course, if we have namespaces that are constrained, we have to pipe them through some authority, whether that is a human authority or, as we know today, like blockchain authorities or whatever. What if we had no authority? What if the authority was cryptography itself? You could you can generate a private and public key pair and use the hash of the public key as a name. It's not a readable name, of course, it's a huge hash, but it's a pointer that you can change, because you can use the private key that's related to that public key and sign records and push them out into the world. of what the name is changing to. So that's what SFS is about. That was the idea. And he implemented it way back. I mean, in a weird way, IPFS is re-implementing a lot of the SFS ideas in a new world and more focused towards the web. But a central and very important piece of technology that predates Bitcoin and predates a lot of other storage systems that were important, that have been important, very important, that have emerged since SFS came around. It just never really took off as a wide thing, but perhaps we can make it happen. All right, the model. So this is important to explain simply because if you're going to hack on IPFS or hack with IPFS, it is crucial that you understand the model, the data model that IPFS has. I just want to focus on two things. One is the Merkle DAG, and we may change this to Merkle Web or something. I like saying Merkle DAG because it is a directed acyclic graph, meaning that you can look at a node and all of its children and know that it terminates somewhere, and that lets you reason about it much better because you can say, let's fetch this whole thing and put it into a device, and now your application can continue to function without having to know which thing you're going to query later. You have that ability to reason that way. And Merkle DAG is how we structure data. So people that understand blockchains know this as the blockchain is a big Merkle DAG, right? So you have blocks that are getting created over time, and they might be pointing to transactions, and all of it is hashed, and you use links that are hashes to reference between them. So that's what a Merkle DAG means. People have been calling these things Merkle trees, and maybe we can call it that way. I see back to people that have, yeah. So we could call it this Merkle trees, but a Merkle tree is also a very specific other thing that using the same name maybe is overloaded and leads to confusion in my experience. So we call it the Merkle DAG. We could call it the Merkle Web. We'll see. IPFS nodes, in contrast, are these sets of there are programs that operate on the Merkle DAG, and they implement the IPFS protocol, which is a series of layers, as I showed before. And they exchange Merkle DAG objects. That's really all you need to know about that. Content, programs. So Merkle DAG and Merkle DAG nodes. The word node is unfortunately overloaded. And IPFS nodes are the programs that actually run on your computer and manipulate this content. And these nodes could be big servers like we see today with HTTP or whatever, or they could be embedded into another application. So we have the ability to embed IPFS nodes into your application. You can use it kind of like SQLite to get really very cool. And in IPFS, data forms DAG, as I was describing. So it's called the Merkle DAG because the links of hashes, and you can think of it kind of like Git and blockchains and so on. And this is what a Merkle DAG looks like. Every single node can have links or data. And this is kind of a straight mapping from the web. Instead of creating our own data structure, we decided to make the most general thing we could find, which is you need the ability to point to other things, and you need the ability to store some data. And once you have that, you can build everything else. You can build Git on top of this, you can build blockchains on top of this, and you can build file systems on top of this. So we layer our UnixFS data structure, which is a mapping of the Unix file system, onto IPFS. It's a set of data structures. So it's a file and a file abstraction with a directory and a directory abstraction, and they are layered on top of the Merkle DAG. So you could construct Git and take the trees and the commits and the blocks and put them on top of IPFS. You could create blockchains and say we have blocks and transactions and other stuff and layer on top of IPFS. You can build operational transforms. You can have a document and updates to a document and layer it on IPFS. So it's a really powerful abstraction. An IPFS node, just to get to specifics, has a PKI-based identity, so every single program that runs has its own public-private key pair. You can sign, so we haven't implemented this yet, but the goal is to have them be able to manage multiple keys, so you could share some other keys, but at the very least, they will have their own. And you'll be able to sign those too, so you'll be able to certify, so if I have many nodes, I can sign another node's public key so that you can see that it's mine or whatever. These nodes connect to other nodes, they store part of the DAG, they exchange parts of the DAG with peers, and they can be run on a server, embedded in applications, and so on. They form peer-to-peer networks. We are transport agnostic, and this is a very interesting thing. There are use cases for programs where you can't actually open a port. You can't open TCP or you can't open UDP ports. So we have the hard constraint that IPFS must work given only a duplex pipe to some other IPFS node. So you could layer IPFS directly on IP. So that can work. And you could layer it on Ethernet if you wanted to. But it all depends on how you're doing your routing system. But we have that as a constraint because in many cases, for example, you're inside the browser, and if you want to run on a full IPFS node inside the browser, you can't open a port. You only have WebSockets or WebRTC or HTTP. You don't get that kind of access. Or if you're inside a Docker container, you could open ports, but they might not be mapped to the world, so you couldn't actually expose them or some stuff like that. So it makes life both harder and easier to create the constraint of being transport agnostic. Harder because we have to work harder to not go and do the easy thing, but easier because it makes it much wider. Like the deployability of this thing is way wider than most systems because of that. Systems can find each other and they route, so that this is where the routing system comes in. The nodes will engage in a routing system, which means that they will self-organize to find each other and find content. And so for now we're using a DHT because that's well known and tried and proven. There may be better ways to exchange content. For example, here we'll actually play with local DNS, and we'll use that way to discover each other. We haven't yet implemented the local DNS as a routing system, but we will do that. We'll be able to send queries for content, and other peers in your network can answer whether or not they have that content. But this, there's a whole bunch of other routing systems that you could imagine, right? Like you could imagine routing systems that are, secure channels and secure announcement channels where you can know whether or not you're being silenced, or whether or not your messages are getting through. Things like secret sharing and so on become interesting things here. They're not good enough to do routing of tons of messages really quickly, but they're good to know that the thing actually is sending out messages. And so this is why we layer, right? Because if you layer, you can swap out later. And the nodes exchange data in a protocol kind of like BitTorrent. It's inspired by BitTorrent. It's sort of like a melding of BitTorrent and HTTP. We call it BitSwap. There's a lot there because you can engage a whole bunch of strategies of how to exchange content. We haven't gotten around to implementing most of what we want to do here, but things like setting up policies for being a node that sort of listens to the routing system and says, oh, a lot of people are requesting this stuff. Cool, I'll go fetch it and then be able to serve it to other people. Or be able to establish notions of trust. We share a whole bunch of data, so cool, this seems profitable. Let's keep exchanging data. Or even things like, I can send this data really quickly to you, but it's going to cost you a penny, right? Or some cryptocurrency. So you can start putting all of these strategies directly into this protocol. And the idea is to establish a common base where it works peer-to-peer based on simple barter of data. Of like, I'll send you bits and you'll send me bits, and it'll work, kind of like BitTorrent. But then open it up to be able to do anything else on top of that, and make all of that programmable. Because then you can do some really cool stuff, right? You could have a whole bunch of nodes that understand Ethereum and say, I will trade you some content for some Ethereum currency. Cool. And you might have to wait for a transaction to happen on the blockchain. Or you might do fair exchange, or you might do you might exchange Bitcoin, or whatever, right? It really opens it up. So this is exciting and interesting. We haven't gotten to implement a lot of what we want here. Right now we have super brain dead thing of just sending stuff. It's totally not perfect yet, but we are headed there. And you pull in the pieces of the DAG and you reassemble it, and now you have it. Cool. All right, so that's the overview of IPFS. Any big questions that people have right now? Because I didn't want to sink into a lot of the details. I did want to establish a common base that everyone can agree on and give you some visuals for how to manipulate these objects. Yeah.
I'm not sure if this is too technical, but one of the big use cases you mentioned was protesters in Egypt collaborating on a document. And you mentioned operational transform as a way to synthesize all their edits. But I think my general understanding of OT is that it's very vulnerable to say a malicious user pushing an edit that says delete the entire document or delete more characters that exist in the document. Is there some way for the network?
Yeah. So I wouldn't suggest that you take up the straight up OT that people use today to do Etherpad or something and say, great, this is now resistant. And even more than OTs, I would think about CRDTs. That is the new hot thing. No, but you are able to construct a data structure that has certain operations. that are convergent by definition, and because they're convergent by definition, you can run the same data structure, or like programs that operate on that data structure that are disconnected, that can do all sorts of edits, that will converge, right? Now, your point is, well, what if people can delete the whole thing? Well, you could make it so that the tombstones, like deletion, requires a signature. So if deletion required a signature, then only certain sets of people could delete. Maybe you can construct a document where deletion requires a signature of the person who added the entry. So you could have a Google Doc where people could only append or delete for themselves. But
that would be at the application layer, though. There's
yes.
no way for the network to enforce that this is a valid, like.
That would be at the application layer, yes, but IPFS gives you a way of constructing that data structure and exposing it through the transport. So think of IPFS as a huge transport where you're only creating each one of those updates, each one of those things will be its own IPFS object, and it will have its own address, and you can reason about moving it around because you can very quickly know this is like the root of some tree, or like some subtree. Take that whole thing, package it up, and move it somewhere. Yeah, so that's why it becomes like, it's subtle, but it's important. It's like HTTP today required all this other stuff on the application layer to even make that make any sense, and we could sync that into the transport. It's like a data structured transport. Yeah.
Two questions, but they're related, I promise. One, have you heard of Xerox Parks Protocol, CCN?
Yes.
And two, with that said, how do you deal with like data if it becomes stale? There's like a new video, new version of something.
Yeah, so a couple things on that. First, on CCN, there's a lot to say about CCN. I found it like after coming up with it. I was like, oh my god, this is great. Also built by one of my heroes, Van Jacobson, who fixed the internet a couple times, I think now. He invented congestion control back when the TCP was just drowning the internet in packets. He went into a room with a whole bunch of reams of paper and said, we need this, and behold, the internet worked again. So it was really a great surprise to me to know that another of my heroes was working on related stuff. CCN is an approach that they're trying to do it, as far as I understand, at the IP layer. So they're trying to change how the entire network moves around computers. And I haven't dug fully into CCN to understand the entire system well enough. I haven't really had enough time, and I want to. From my take on this, I think that's the right idea. I think that we should be moving in that direction. The problem, though, is that replacing IP is really, really, really hard. And they are totally, if I remember correctly, they have an implementation that will work, where you have a subset of nodes that run CCN, it'll still work, and will still pipe through IP when it has to. And over time, you can tip the balance. From my point of view, CCN is not, or content addressing in general, is not going to be a thing until applications demand it. Until applications say, we have to make the network use content addressing. And we can't get there until it becomes relevant to applications to do things this way, which means applications at the very top layer have to reference these objects using these things. And from my point of view, that is much closer to replacing how the web works, or rather patching how the web works, than it is about replacing the entire internet infrastructure. And I think this is a way to get to CCN. Actually, when I saw it, I was like, oh, this is awesome. We can construct a need for CCN. And once people are changing content this way, because we have to do all this crap of figuring out all these point-to-point connections between computers and transport agnosticism and all that kind of stuff just to be able to exchange documents or data structures. And CCN says, no, let's put all that content through the pipes and do, it's a really beautiful idea. And so IPFS will just layer really nicely over CCN, and we'll do a ton of really hard work for us. But we can't get there until we convince the rest of the world that this is a good idea. And the way to do it, these are optimization problems where you have the entire world, massive organizations moving extremely fast using some technologies and inventing, and you have to demonstrate that this is useful for them now, and they'll start shifting, right? And if you just come in with a whole new worldview and say, hey, behold, beautiful new thing, they'll say, cool, we are doing this other thing that's useful to us now because we get just a little bit more money today. And these systems are very hard to move. Think about linked data. Tim Berners-Lee had this amazing idea of saying, why don't we just put all these data structures on the web, and it's all linked, and it's all beautiful, and it's all wonderful, and we'll be able to compute very easily. Except that it hasn't become true fully yet, because it is difficult to convince organizations that this is the right way. it has a whole bunch of like problems, or that conception of the tooling. It's mostly the tooling around the idea that isn't perfect yet, which is why only Google and Facebook and Wolfram, I think, have constructed really good semantic webs today and linked data webs, but they have them all proprietary, right? From my point of view, linked IPFS is a good way to like make linked data a thing because you can you're linking all the data and exposing it as a data structure. But it really has to be high performance. It has to make business sense to huge organizations. And if it doesn't, it's not going to happen. Or it might, but it's difficult for it to. So that's my point of view. Could be totally wrong. All right. So any other questions before we move on to the like brass tacks? Yeah.
You mentioned something earlier about the possibility of somebody sitting on the network and just listening to like people who are trying to look for some bad file or something like that.
Yes.
Can you talk a little bit about ways that
to mitigate that?
To deal with that?
Yeah. So yeah. By the way, so IPFS is alpha software at the moment. Like, do not use it expecting anonymity. Please do not do that. Please do not. Don't. Stress that out. We take security very seriously, and we're not going to call anything secure until we know it is. So we have some crypto in there, and like, we haven't fully checked it. We haven't audited it. We know that it's probably wrong. So don't assume that it works. So we're very clear about that in like our security notes. In terms of making it so that people don't announce, or being able to deal with that problem, so that is several layers, right? One of them is that your routing system is at fault here, right? Like it's how you're doing the routing of the content that matters. So if people are listening to it, it's because you're advertising and you're asking local people for what that content is. So if your node is doing that, it is only natural that an eavesdropper could listen to it. So this suggests that certain kinds of content you don't want to route through a local DNS routing system where anybody can listen to it. Certain kinds of content should only be routed through something, say, like Tor, where you have more guarantees around anonymity. You can think, so IPFS is both transport agnostic and multi-transport, meaning that you can have multiple transports plugged into the node. Or ideally, you would actually just generate another node that you have no relationship to whatsoever, where the keys are not linked, and that node you would use to talk through the network.
Like a proxy.
It's kind of like a proxy, where like you know that it's yours, but nobody else does, and you pipe all of it. You set it up so that it only routes content through Tor, or it only routes content through something else. I mean, Tor also has problems too. Like I actually don't think. I was thinking about this today. Like, I don't think we actually have anonymity on the web or on the internet. I don't think it's there yet. I think we have obscurity to some extent, which is kind of like really bad from a security standpoint. You never want obscurity to be the reason why things are safe. But we don't really have anonymity.
Because IP addresses are tied to physical locations, which are tied to people, right?
Yeah, and I think just how you access the network and what you can listen to. I mean, if you really want anonymity, I think we have to go all the way to like randomized access, like randomly throwing packets everywhere so that content can be. There's a ton of work on this in the cryptography community around doing oblivious RAM, for example, like having random memory in which you can do accesses that doesn't leak information. So you can have a whole bunch of data that's encrypted, but just by looking at when you access stuff, people can leak out information. So that's scary. And the solution to this is to do a whole bunch of other accesses to try and hide the fact that you're doing these accesses in the first place. And so maybe that suggests that perhaps networks, if we really want to go towards anonymity, we can start doing things like that. And I mean, like I think like the Tor solutions are really cool, right? Like you're able to just within the Tor system, you're passing content across a whole bunch of sets of people where no one node in the intermediary places knows where the messages are going. It's how do you get to Tor in the first place, or how do you get out of Tor, right? Like there's all these papers that talk about, or revelations that talk about how easy it is to like spy on the edges of Tor and correlate messages. So yeah, I think that there are solvable ways, but it has to be done carefully, and it has to be done kind of step at a time. And on this, I actually think we're going to need buy-in from some of the bigger, large engineering efforts, people like Google and people like that actually do care about our data. The problem is, there's like currently the business models of a lot of these companies rely on access to data, and so we're going to have to come up with a similar or a different deal of how to do that, right? Yep.
So how do you deal with not accessing banned data, but having banned data without wanting to?
Oh, so IPFS does not give you any data that you don't explicitly request. So this is why IPFS on its own doesn't have reliability, right? So you can't add data to IPFS and disconnect and expect the data to survive. IPFS is a transport. It has a transport with permanent addresses, which you can use to give data permanence, but you need to trade a resource for that, right? In order to get a whole bunch of people to agree to keep your data for you, you have to trade some resources. So there's some networks out there that do it by sharing, like shared pooling, or by doing I think Freenet does this, where you all store each other's data, but accesses are really slow because you don't want to show who has what. I think that those kinds of systems have a very specific model about how to move around data that don't lend themselves to some of the use cases that we care about. For example, booting VMs really quickly inside a data center, where they don't really care about anonymity, for example. And so IPFS is a transport for how we express these data structures, how we move them around, and how we get that you can then use to build other systems on top that pin the data, right? So if I wanted something to stay around, I would create it, and then I would either run a node or ask other people to run nodes that pin my files or pin my data structure. Yep.
So does IPFS reveal the IP address of the node that you're retrieving data from?
It depends on how you use IPFS, what transport you're using it over. So today, the code that you're going to download today uses TCP. So yes, in that case, you are making point-to-point connections to people. So this is why it's not anonymous.
Yeah.
Yeah.
So let me give you an example of an attack that I have in mind.
Well, I don't want to go through. So I'm happy to take that attack question if it becomes interesting to other people, but I also don't want to dive into too specific of a topic.
Maybe we can go through the demo. Starting your demo here. Sure.
Yeah, I don't mean to cut you off, and I'm interested in that, but I also don't want to sidetrack the whole thing. Any other questions before we proceed? Cool. All right, so we're going to install a node, we're going to run it, we're going to stream some media, we're going to publish our website, and we're going to boot a VM. All right, are you excited about that? It's cool. For best results, it's ideal that we're all on the same network. So if you are using your own, your own Wi-Fi or whatever, ideally just connect to the one here so that we can use. And hopefully they have local DNS set up. If not, we'll find each other through the DHT. But it should work. Cool. 3 ways to install IPFS. If you have Node, npm install -g go IPFS. If you have Go, go get github.com/IPFS/go IPFS/command/IPFS. It's very long. Or 3, install packages from the website. I will show you that one because will work no matter what you have installed. Actually, not no matter what. You need an HTTP browser. And I think you all have that. So take your browser and point it at ipfs.io, and you will see a web page that looks a lot like this. And you'll see a big button that says, well, a small button that says install IPFS. And you click it, and you'll see some pre-built packages. Hopefully, Go Builder will work. I don't think I have a screenshot of that one, but it should download it straight up. Yeah.
Are you going to secure those downloads?
Yep. Right now, it is running on HTTP, not even HTTPS, because GitHub Pages doesn't have HTTPS, as far as I understand. So we're gonna move off of this, and we're gonna self-host completely. We've been waiting to get IPNS. IPNS is our naming system. Sorry, I got disconnected. So we want to completely self-host, and we're gonna do signed releases, but that takes a little bit of work of making sure that I have keys in a specific computer. not that I'm going to delude myself into thinking that not all computers are owned, but you know, there's barriers of entry, right? And so I'm going to get some of the, like another of the developers and I are going to get some devices that we can use to sign the releases, and then we're going to self-host all of the releases through IPFS. So you'll have like the actual publish the hashes as well, so you can check the whole thing. But you know, we are compiling with straight up Go, and we are compiling with stuff. So I mean, it's better than like HTTP with no security, but you know, trust and trust, right? Yep.
Are other people on Wi-Fi? I'm trying to follow along here. I don't see Wi-Fi passwords.
Oh, yeah. The Wi-Fi password, I have it here. This one. That should work. Cool. All right, so if you install a pre-built package, that should download a zip archive. I don't have a screenshot of that, but I can probably just walk you through it. Anyway, it has a binary, and you move it into the right place. Does that kind of make sense? Pretty good internet. So IPFS, click one of these things. We could actually like download it from me, but we'll do the whole thing, and then you'll get a zip file that you unzip, and you move the binary into the right place. This will be a little bit easier because we'll have like install packages pretty soon. But for now, if you want like the really sweet experience, hopefully you have Node or Go, and it does all that install. Cool. We need to update this. We're now at 0.3.1. And all right, assuming that people have it now, you should have a tool where you can type IPFS on the terminal, and you see this coming up. And IPFS is not just a command line tool, but we decided to start there for a whole bunch of reasons. Like, we're building a huge tool set with all these different components. There's this binary, which has a whole bunch of different commands, kind of like the Git toolchain. There are services that run, like we have a set of HTTP gateways that are open and receive, I'll show them to you how they work. There's other nodes that do other stuff. So we're making this huge ecosystem of tools because different use cases demand slightly different things, and we want to support a whole bunch of them. And when you sort of create like a new world, you have to go and like do a lot of these things. And we are very strong believers in Unix, in like the Unix principles of design, which is small things that do one thing and one thing only. Someone will point out that we have this big, massive binary that does everything. But it's decomposed in the code, and it's decomposed in the ideas, and you can build different implementations that are all slightly different tools, like in Git. We chose the one binary approach because that's the Go model, and that is just faster than doing it the other way. Yeah, so instead of building libgit later, we decided to go like straight there. I guess if that makes sense to anyone. And so now you have IPFS, you can init. Let me see if I have a node here. Yeah, I do. So let me clear my node. Can everybody see that, or should I make it bigger?
Bigger, yeah.
Yeah. You can type IPFS, big commands. You can type IPFS -- help with any command, and that'll give you, help on that one. This one happens to be the same. So you can do IPFS init. Let's see help to see what's in there. We have options like passing it bits. For now, it's only generating RSA keys. We'll move to ECC soon. It just was easier. And it'll also be pluggable, so you'll have be able to choose different algorithms, and you can force it. So let's say init. So generate key pair, cool. And I get a pure identity, which that is the hash of my public key. The formatting will change a little bit later on, so don't get too attached over these keys. You'll see that we have done a little bit of proof of work almost to make the hashes of some keys start with certain prefixes. Yeah?
Are you going to, you said the formatting is going to change, so are you going to specify the hash function in the
Yes, exactly. We're going to specify the hash function and specify so not only that, but if you can tell these two hashes start with QM, that's because we're using a format called multihash, which in the hash digest itself specifies the hash function, so that we can build tools that understand which hash is which. So if today you wanted to upgrade Git to make it use SHA-2, you could recompile it, but that would break tons of other scripts that assume that a Git hash is of a particular length or is a particular hash function.
So you're already doing it?
Yes. So that's the format of the hash. I'm saying that the format of the key data that the format of so the key is some amount of data, right? And it has some formatting around it, and that might shift a little bit, which would cause the hashes to change. That's what I mean.
Okay. What is that hash scheme called?
Multi-hash.
Multi-hash.
Yeah.
And that enables you to have specific types.
Yeah, so multi-hash, in fact, we have a little tool called multi-hash. And what right now is waiting for standard input. So that gave me a multi-hash of so this, and multi-hash, you can say multi-hash dash help. So this is not probably installed in your computer because we haven't installed it yet. But it has a way to do different hash functions. You can add, you can check some stuff with it. You can choose different encodings, and so on, right? So if I go foo into multi-hash, and we do dash dash, so dash A for SHA-3, I think that should work. Great, so now I got a SHA-3 hash. And it's prefixed slightly differently. So, and then we can do SHA-3 encoding E raw. This will be like the actual binary digest. We can do hex, so we can get a hex output, and so on.
Shall we demo dash A, SHA-3, and SHA-2, just so that they see the prefix changing?
Oh yeah. So SHA-2, 256. So we say that because you can do SHA-2 512. And you see the prefix change there?
Yeah.
Oh, and get this. So you can do L, which is length, and say 256. I think it's in bits. So check this out. So we can do 256. Two hashes, same length, different algorithm, because one is SHA-2 512, but they have the same length. But thankfully, the prefix of the hash tells you which hash function it is. The 20 there is like the 20 bytes. So a pet peeve of mine is that people will build systems with SHA-2 256, and they'll realize that some architectures compute SHA-512 faster, so they'll just switch the hash function, but not really tell other people, or not document it anywhere. And then people will be trying to, the hashes won't match, right? And so this is why we came up with multi-hash. And we have also Multiaddr, which these are all my local addresses, and you see that they specify the protocol of the address, because again, that gives you independence. Sorry, these probably won't work on your machines yet. We probably will make it like a toolkit, and you can download all these pieces, but it's available with Go. All of these have their repositories. So if you go to jpanet/multihash, that is a format. Some people have been making implementations. We have a Go one, a Node one, someone made a Clojure one, and a Rust one. I think the Rust one got added recently. Go, Node, Clojure, Google, Rust. Yeah, cool. So that's multi-hash and so on. We have a whole bunch of code. Back to, let me re-init my, so we get back the content. So what's here? So this was, the peer identity, right? And you can actually do, let me just copy this so I have it. You can do IPFS ID. So if we do IPFS, we'll get like a listing of commands. Down here in network commands, you see ID, show info about IPFS peers. So if you do IPFS ID with no argument, it'll show you your own ID, which for now is defined to be your ID, which is like the hash of the public key, shows your actual public ID, shows some addresses. Right now it's null because I'm not connected to the network. Shows the agent version and the protocol version. Agent and protocol are there because we will have many different implementations that will all change, and we'll implement different versions of the protocol. And we haven't decided yet, but it appears that we will be following semantic versioning. So with protocols and everything, so that you know if you're not familiar with semantic versioning, then read about it. It's a cool way of knowing that the version implies certain things about what still works and what doesn't. Like you update the major version every time you do a breaking change. Anyways, in that init, okay, one more time. I got, to get started, enter IPFS cat, this huge path. So this path is our concept or our notion of a URL, or a URN really, because it's not a URL. It has begins with /IPFS / and then there's a big hash of something, and then there's README. So what that means is that you're going to use the IPFS protocol. It's an IPFS resource. You're going to use this particular hash as the root, and you'll fetch inside of it whatever is linked as README. That means that this is actually, so if I do IPFS object links on that hash, I get back a listing of the hashes in there and the names of the link. So if I do links of that /README, I think this works, it might not. Yeah. Oh yeah, that did work, it just has no links. I don't know if people see that, I added a /README at the end. I could do another one of these hashes, IPFS object links at another hash, and it has no links. That means that it has a bunch of data. I can do IPFS object data and pass in the same hash, and then I get some data out. Cool, so this is like a very low-level plumbing command, right? Yep.
So is that illustrating like the navigation of the Merkle DAG?
Yes. So IPFS object, which will rename to IPFS DAG, or IPFS web, one of those two. IPFS object, for now, shows you the navigation and listing of the actual objects. So the data command pulls out the data piece of the object, and the links command lists the links in a nice way. You'll notice that there's a little bit of crap here. What is that? That is some formatting that's around this object. So we can also see, so we can actually just ask object get, and this will pump out the raw data directly. And right now it's encoded, this one is encoded in JSON because it's nice to us. So you see the links, it has no links. You see the data section, and it has some stuff at the beginning. That's that formatting that you saw. And then it has like some data in there. We can ask for encoding. I think this is the format, protobuf. And this should have given me a protobuf at the beginning. Yeah, so this is actually a protocol buffer. So it outputs protocol buffers. You can actually, if you want to go and be, as a friend of mine put it, enterprise ready, you can go and ask for XML. So it'll give you XML. Cool. So this is the navigation of the DAG. So JSON is more human readable than protobuf, so we'll stick with that for a bit. And this is slightly different from what it told us to do. It told us to do IPFS cat. I don't know if you remember. We can do it one more time. It initialized key pair, and it said, run IPFS cat, this whole bunch of stuff, right? That means, so cat will probably keep it there, but cat is doing something more advanced than object get or object data. So object data will be pulling out the data of the file. Cat is saying, for now, it's using the UnixFS data structure that I mentioned earlier that is representing Unix files. So some of that formatting and some of that crap that you saw was a little bit of wrapping around the object to describe that this is in fact a Unix file. So IPFS cat understands that these are files. And the reason it's relevant is because if you have a really big file, we'll do something interesting. I'll show you in a sec. So IPFS cat will show me no crap because it'll pull out just the part of the data that's the file. Great. If you're seeing this, you successfully installed IPFS and are now interfacing with the IPFS Merkle DAG. Cool. Warning, this is alpha software. Use at your own discretion. It is actually really stable. It will not eat your data. People are already using it. We're already using it for a lot of stuff. We're already self-hosting. So it's good. It's just that we don't want to say use this for production or use this in any, don't rely on this yet. Yes?
So what's the first hash?
The first hash, which first hash? This one?
No, this
This one.
Yeah. No, yeah.
This one.
Right there.
That is a directory. So when I did IPFS, so cat/readme, it said go to that one and then follow the path, do /readme. So that means pull out this object here. See?
So the README is not content address.
It is. We're just resolving it through the directory. We're telling IPFS, hey IPFS, fetch the hash qmcqtw, and so on, which is a directory. And inside of it, look up readme and give me readme. So in there, it looks up readme and it gives this other hash, and then it
Every time you read, you're reinitializing it. Is that the same? Is that hash be the same?
Yeah, it's the same thing. Yeah, yeah. So you can do IPFS cat directly on the hash of the readme file and pump it out the same way. So, you know, A.
Hash is the head of the Merkle DAG. It's the hash at the top level.
I think this will make more sense. So I did IPFS cat of one hash into A, and cat of the directory /readme into B, and we can diff A and B, and that's it. Yep.
Does readme have a hash?
Yes. So if I did, when I ls the directory, this is like if you're doing ls in your directory, right? Like ls-l. This is the same thing, right? LSL and IPFS ls are meant to be the same thing. You're listing a directory, which means show me the objects. And in the file system, in the Unix world, we could actually list out the inodes. I don't remember how to. There's some command that shows the inodes. Dash I? All right, cool. Yeah. Thank you, guys. So that's the inode, right? This is like the old school Unix way of like addressing things. And so in a way, you know, IPFS ls is doing the same thing, but these are cryptographic hashes, which means that they can be accessed anywhere.
How does it know to interpret that hash as being a directory?
Oh, because I said IPFS ls here. So if what would happen if I said ls on README? Well, README doesn't have any links, so it pumps out nothing.
So do you do like IPFS object get on the directory?
Yes. Sorry, I will grab the person that graciously raised their hands. So you can do IPFS get on the directory, and this shows me the JSON output. It has the links in there, about, hash, size, and so on. And it'll have some data in there. This data is specific to the directory formats in the UnixFS data structure that we have. And it's what contains a little bit of extra information telling you that it's actually files in there.
So when you hash that whole, so when you, the hash of that directory is actually the hash of all the data in the directory? Is that?
The hash of that directory is the data in,
Because
yes.
a directory doesn't make sense. There's nothing there.
No, yeah, there is stuff there. It's the links. The directory has the directory entries. The data of the directory, or not the data, but like the stuff in the directory is the links. So the hash covers the links too. This is what constructs the DAG, like get.
To a directory, then the directory changes.
Yes, exactly. Yeah, think of it like Git, right? So when you use Git, it has a Merkle DAG inside of it. It has trees and blobs, and if you change a blob and add it and commit it, it will create a new blob, and its hash will change, which means that the tree pointing to it also has to change. We have to make a new one with the updated pointer, and then if you commit that, you'll create a commit object. And so this is why you create a huge, amazing tree that you can replicate and distribute, and so on. All the magical goodness of distributed version control, which is what really this is, right? This is a distributed version control, but for the web at large. Yeah.
So the hash of the directory is actually the hash of this object that you just got.
Correct. So it is the hash of this object, not with this format, because this is expanded JSON. Let's see if we do encoding equals protobuf. This might, and we do multi-hash. I think this, yeah, so check it out. Oh my god! Right? Unix, man. Unix. So good. So good. Yes, so all of our tools work this way. Or most of our tools work this way. And we're improving them all the time. Like, there's a lot of stuff that is still very raw, partly because we're trying to move really fast on a lot of things. And you know, we're not, there'll come a day when I'll say we will not break user land anymore and we will not change things under you, or if we do, there will be very good reason to, and we'll be, you know, we'll do proper release notes like Git and all that kind of stuff, with like long warnings before. But today is not that day, and today we get to play around with the interfaces quite a bit. So if you write scripts on top of this, check that those will work for now. But things are really stable. We only break things if absolutely necessary. Yep.
So just some feedback.
Yep.
Calling it a directory I find to be extremely confusing, because that's not how directories behave. So maybe call it something else.
That is how, I don't understand why that isn't how directories behave.
In a directory, you can change what's inside of it. You're not actually changing what's inside here. You're creating essentially a new directory on every file change.
Yes, exactly.
And that's not how directories work.
That is how directories work in any content address file system, like Fossil, like Venti, which I guess Fossil and Venti were the same thing. I think Tahoe LAFS does this too, or Git does this too. All of these file systems are content address. SFS RO, which I just learned about today, which I guess we re-implemented in many ways, does the same thing too.
Okay. Well then, I guess, yeah, maybe like in your docs, call it a content addressed directory.
It is a directory. So like in file systems, when we have this abstraction of a directory that's like POSIX compliant, and that's useful when you want to interface with the world, but if you dig into what a directory means into XFS, it does the same thing. XFS, which has directories, are all content address and use hashes, and they call them directories. It's the same thing. So it's like yeah.
Can I try?
Sure, yes.
Okay, so you take any data structure that is mutable, and you can make an immutable version of it that on changes just hands you a new copy that is the new content.
Yes.
So it is irrelevant whether it's a directory or a tree or a list or whatever. The way you make a data structure immutable is whenever you make a mutation, you get a new one.
Yep.
So if you were to follow the link to the folder before you made a change and see the pre-change version. So like you change it and it changes the directory.
Yes.
But you still use the old directory. If you see what it looks
It's still there. So
you see what it looked like before you added the file.
yeah, let's do it. So make dir foo echo bar into foo/b, and we'll echo other stuff into C.
You're missing direction.
And we'll do IPFS add -r on
Missing the direction
foo.
then.
Oh, sorry. Sorry. Cool. And we add -r on IPFS add -r on foo. And that added foo and the stuff inside of it. And we can IPFS ls this hash, and we'll get back, qmtz, that's b, and we can IPFS cat this hash /b, and we get back bar, right? That's like super basic, right?
Can you do the bottom of your terminal up like 25%?
Yes, actually, I can. We have the technology. 25%. 25%. There we go. Is that good enough? I can move more. All right.
So maybe do another echo into one of the pre-existing files and show the add, how it differs from the earlier add. That different content. Oh, then you add a file.
So now the hash of the directory changed. C and D have the same content, so it's the same hash. And that changed. All right, sounds good. I want to move to like the cool stuff soon. But does that kind of give you a sense of how we're constructing the Merkle DAG? Oh, and we can look at it. We can say graph MD, and thank you. I also think it's cool. Not everyone thinks Merkle DAGs are cool. I'm glad I'm amongst friends. We can take graph MD, which pipes the output in dot format, and look at it in the browser. Whee! Oh man, look at that. Those links go to the same node. It's the same thing. It's so good. But what if we, you know, that whole thing that we had before, where was it? This graph, MD. Does that make more sense? Cool. Now let's do something more ambitious, like have this basic directory with some stuff in it. So I had this basic thing in there, basic, which has like a picture and some directories and stuff, and it hashed it all nice like that. You can tell by the fact that these hashes are the same, that bar and bast/b are the same thing. You can tell that f and foo are the same thing over here, and so on. But we can see it, so not over here. If we run, so what if I wanted to see, oh, I can show you, I'm gonna start the daemon on, which means that, so I will start it up down here, and so that we don't have to see it, and when the daemon runs, so I guess I'll make it seeable for now. It starts a network service, and it says API server listening on blah, this is a multi-adder. Gateway read-only server listening on blah, this is another multi-adder. Which means that we now have an HTTP API where we can issue commands to the node, like cat. So let's do IPFS, so actually curl, we can use curl, localhost, let's see if this works, /, things API, v0, this is all documented somewhere, I think. And we say, so if we do /version, you can test that it's an IPFS node. It'll tell you the client version and the protocol version. If you do API /version0 / object/get, I think this should work. And then we say, or object, yeah, object get, and or actually ls, we can just do ls directly. And we say arg equals, and we pass the hash. Shit, I lost it. I'll add another one. Arg this, boom, I get some JSON back. And it tells me objects, there's a hash and stuff in there, and it's that stuff directly. So you can manipulate the entire IPFS node directly from HTTP to localhost, right? So this is like localhost. You have a full API that understands JSON, protobuf, and XML, if you want XML. I'm going to stop bashing XML soon. And it will, output it to the terminal. So you can use curl to control the node, which means that you can run this daemon and then write whatever tool you want in whatever language you want, and you'll still control it, and it'll still respond to the exact command line interface is mirrored with the API, and we're extremely careful about that. Nothing changes. So anything that works locally in the CLI will work on the daemon, except init, because you can't init a node before it's running, or you can't run the daemon on node before it's initted. Yeah.
What's type in this? What's the
oh, type. So that's not supposed to be there. We will remove this. I'm obstinate about there being no types here because they're in the wrong place. Ignore that type being there. I don't know how that's not good. There was a pull request that we merged and then we reverted. So type is not supposed to be there, but we can do other stuff through anything that we can do in the command line. And now that the daemon's running, if I do IPFS ls into the same hash, I'll still get it all work the same. But now, because you don't want to do multiple access into the same repository, the command line is piping the commands through the HTTP API to be safe. But it's all transparent here. So now that we have this daemon running, what else can we do? So there's this API that allows me to do anything, and then there's this other gateway thing. That gateway is an HTTP gateway. I guess we should say HTTP there. We go to localhost 8080, and we ask for that directory /IPFS. So if we do version on the gateway, we should also tell us that it is a proper gateway. There we go. Woo. And if we do /IPFS /that, gives us an ugly index. This is like HTTP 1.0. Actually, I don't know, maybe even older. And we can click links, and we now have it. But that means the fact that I'm connected. So this gateway right now, we have we're exposing everything that is available to IPFS as a node. We're exposing all of the objects onto HTTP. And here's a very interesting case. So in this directory, we have this thing called treeincosmos.jpg. Treeincosmos.jpg is one of my favorite pieces of media ever. Look at it, it's beautiful. However, you'll notice that if we look at the graph of this, this huge, where's treeincosmos? Here, treeincosmos is this. This has some links. So why? Why does it have some links? Let's inspect that. Let's say IPFS object get this hash. So I get back some links, name, hash, size, and so on, and no data. That's weird. So if I did IPFS object data that into like tree.jpg, I would get like a bunch of crap that should not be renderable by preview. Why? But if I did cat, if I do IPFS cat on that hash, and I open it, boom. So what's going on there? These pieces are blocks of data that when concatenated, so check this out. So let's tree.jpg. Let's take the next one. Let's cat tree.jpg. So I'm appending to it. Let's take the next one. Actually, let's look at it now. See what happens. Oh! I'm having a lot of fun because this is cool, but like, there's a lot of cooler stuff that you can do with it. Let's try let's mess with JPEG, right? Let's do things like catting it into the wrong order and catting it twice or something. And of course, this is not going to make any sense to things because we just took random blocks and like rearranged it. So JPEG is going to freak out. So yeah, it doesn't work so well. But we have the header right, so that's all well and good. But wait, doesn't this mean that when we create a format for a file, like tree.jpg, and we have some knowledge about how this format should be structured, that we could reason about how to construct IPFS objects for it and put the right pieces in the right place? For example, if this wasn't a JPEG, but it was like a huge VM or something, and we knew that portions of it were going to change very much or something, we could put those in specific independent objects and be smart about how we construct the objects so that we use deduplication to the most advantageous position, right? And we could do things such as carefully, if we know that it's a JPEG, look for the boundaries of pieces and only breaking on that, and do things like that. So that becomes possible. Again, won't demo to you today, because we're not there yet, but it makes it possible. Any questions so far? Keep scrolling this. Yep.
So you said there's no typing at this level. So in the DAG that's here, is there really?
So why is it that when I cat? So great question. Why is it that when I cat this file, it worked, right, but when I looked at the object, it didn't? That's because we are cheating a little bit. IPFS cat and ls understand the UnixFS data structure, which when cat, this is actually going to turn into IPFS files cat, because files will be our word for UnixFS, because you probably don't want to type IPFS Unix cat.
But so is there something in that data section then that's saying
yes,
interpret these links?
Yes, there is something in the data section that's saying interpret these links as a file, which means that you're going to take all of these blocks and concatenate them together.
Okay.
So the basic operation of a file in UnixFS is concatenate. However, that also opens up the door for what if you could do something else with that? What if you could have a file system that interpreted these objects and the data segments of those objects differently? So I think I broke it, but I used to have source GitHub. Now moved it. Command. Oh, it's not there anymore. Is it in Scratch? JSFS. Oh my god, tell me there's a binary in there. No! This won't build anymore. So JSFS, it was using UnixFS, but then it did the last object interpreted the contents as JavaScript and ran it before outputting it. So you could put a function in there, compute it, and pump it out. So that you could do a command like JSFS cat some hash, and it would interpret it as JavaScript, run it, and output it. It's cool, right? And so you could imagine writing more things like that. We are going to be building a, somebody probably has done the work on this already in terms of creating a language. I think ideally we would have a language in there that all these objects could understand, that could define pure functions that we can compute on data with and compute on these objects and really generate anything. It seems like an oversight not to put that in now. And it seems like something that we'll regret like decades from now. But so we're going to be searching for a good language like that and implement it or put it in. And we'll have ways to reason about an object whether or not it has that language. But I think it's one of those important things that if we put it in now, it gives us this like computable layer right in the data, which is amazing, right? You can do you can have a hash that represents pi because it gets into the complexity of the stuff, right? Because pi is this huge infinite sequence, but you can represent it as a function. So pi could only be a few bytes long. That'd be awesome. So yeah.
What's the difference between that and simply catting the JavaScript and piping into like Node?
The fact that the IPFS node, every IPFS node would do it. If you had a computable language there at the very bottom, like one simple computable language, it could be LLVM or it could be something way simpler than that because that's complicated. If you have any language at that layer, it means that you can represent anything. If it's Turing complete, you can represent anything, which means that you can install software by giving you the instructions of how to compile it. So you could ship someone the code in IPFS, you could ship someone a compiler and just run it, and it would, on access, find it, compile it, build it, run it, which would be amazing. So it gets into like the mad science of like connecting all computing devices with a file system that happens to be computable, which would be really cool. Yeah.
On that front, there are some guys on the East Coast, Arthur Brock and Eric Harris-Braun, who are working on a project called Metacurrency, have been for years. They may have made some solid headway on that.
Awesome.
So put you into it.
Thank you. That'd be great.
The Metacurrency project.
Scepter. Is there a new project?
Yeah, Scepter.
Scepter. Yeah, so by the way, I'm sure that the literature is full of stuff like this. Like, in fact, most ideas that we've come up with, even if we've come up with them, I am sure have been invented many times over and are in the literature. So we haven't really thought about this yet. I mean, we haven't trawled the literature and found all of the right ways of doing it and then picked one of those because I'm sure it's been done.
I'd be on that theme there of duplicating things. I'm sorry this is kind of slow, but I didn't quite catch the gist of this, your excitement over this computable objects. I mean,
yep.
If I go in Unix there, I mean, some files are binaries, they're executable.
But if they're executable, that means that what they're carrying inside an executable is a compiled binary for the current computer in the computer that you're accessing the files in.
Yeah, I mean, you can have interpreted languages. I mean,
but you still need the interpreter installed in your computer. So what this basically means is let's put a very simple interpreter as like the last resort at the very bottom that's going to be like totally brain damaged and very slow or something. And let's have that in there as a hook to install anything else in the future. So what this allows us to do is that at the end of the day, we can take something like really complicated, like a whole x86 machine, and compile it down to, and have a mapping between that and that has a VM and an emulator, and we can take the source code of the emulator and at some point have something that compiles down to that language, and so we can run the whole thing. We can run the emulator and compile and run the emulator that will then take the VM, the x86 VM, and run it, which achieves like one of the things that Vince Cerf has been talking about for like years now, which is as time goes on and we evolve in our computing devices, we break everything, right? Like all these old machines don't work anymore. All these old data formats don't work anymore. So resuscitating these old things to try and pull out data is a huge effort. So very recently, Alan Kay actually went back and resuscitated this whole Smalltalk system with a whole bunch of other people to try and pull out and show and run it in an emulator to demonstrate some of the amazing things that Smalltalk was doing then, which, by the way, is a mind-blowing video. You should check it out. But that was a huge effort, and Vinsurf is terrified that, like, at some point we're gonna have like some natural disaster or we're gonna do something stupid, and we're gonna lose half of our machines, and we're gonna lose the ability to understand the other half or something, right? Like we're gonna lose the ability to pull out data from very critical pieces of the infrastructure. And so if we started to say no more, like in the worst of all cases, we're gonna use this brain damaged, stupid computable thing that will always be there. And we make sure that everything else we generate can hook into that, then we can emulate any device ever, and we can look at any data format in perpetuity. Right? So I really care about the future. Make sure that things, yeah?
It sounds like what you're talking about is Mike.
Was that?
You want to do Mike, or you're using
so yeah, so it is kind of like a bytecode, right? But it doesn't have to be as like, for all intents and purposes, it could be like a 5-character language, like a Turing-complete 5-character language, right? As long as it's Turing-complete, it can do anything.
I mean, that's what bytecode is.
Yeah.
A small subset, it codes for a small subset of functionality. You can build anything out.
Right, exactly. So then all IPFS implementations would be required to just do this one thing, and then it would be fine. So between bytecodes, I prefer something like LVM because it's pretty like cool and high performance and so on. And there's already all these backends for it, so we might choose that. But that might be a bad choice towards the future. I don't know yet.
I originally wanted to ask: is there a blockchain anywhere in
IPFS? There aren't blockchains in IPFS. You can make blockchains on top of IPFS. So you can create objects, right? A block is just an IPFS object with links, and the links are like one of them will be parent, and it'll point to another block, and like transactions will point to like a directory or like something like a directory with, integer offsets that will point into like each transaction, right? And like at some point you point to like an identity, and hey, that identity could have like wallets across different blockchains, for example. So in a weird way, IPFS is like this like IP layer for data structures. Yeah.
Do you have a thing that works in the browser yet? Like you mentioned WebSockets tunneling out.
Yeah. Well, it doesn't work on the browser yet. Like we don't have IPFS running on a page yet because we haven't made the Node implementation. I actually started writing the Node implementation, but I ran to go. It's on our high priority list. Like we really want to do this as soon as possible.
Is it possible?
Yeah, why not?
I don't know.
Just JavaScript. It's Turing complete. JavaScript can do anything. Anything you throw at it, it can do it, and it'll do it fast because the JIT is amazing.
I'm just wondering if like there would be bumps in the browser.
Oh, yeah, I know. I'm just harping about the a lot of people are very negative on JavaScript. I particularly like Go more, but I also like JavaScript. I like all these languages. The point is, we'll have an implementation in Node that will compile into an IPFS.js, and you'll be able to drop it into a page and then run nodes on there. So we can get to some of that cool stuff now, as I've been trying. So there's a gateway, right, that's over here, showing us this stuff. So yeah, we have some stuff there. I always show you the picture. What if we could do some video? Do you want to do some video? So in here, I have this file that if we IPFS cat this file here, it'll right now. Oh, I forgot to tell you. So this whole thing is now connected to the network. So swarm peers, boom. There's a whole bunch of peers in here, and I assume that this is our network, and we have found each other. Some of us are here. Hello, comrades. I shouldn't say comrades. Yeah. Hello, friends of capitalism. Blockchains. I care about money. So all these peers are in the network, right? And so some of those are in here locally, and some of those are connected to the rest of the world. And check this out. So I'm going to go to localhost 5001 and go to /webui, which is a, for now, blessed route. So 5001 is the API. If I do that, I'll get this page. And that loaded really fast. I don't know, some of you guys must have had it in here already. So what that did is that it took that hash, and that hash is a directory, so I press ls into that. It is a directory with an index.html and a package.json and static. And that means that that index.html, the browser will just understand it like any other page, and it'll run it. And so this is a full distributed web application written in JavaScript in React components, actually. So, you know, newest, hottest stuff in the web world. And it's a full like HTML5 web app that is just got added to IPFS. It's now working distributed. And somebody else had it in here because I got it really quickly. Like I didn't have it, and it got downloaded and installed. And so now I could actually like disconnect from the network, and it would still be there. But let me show you some of the cool stuff before I do that. These are the peers that I'm connected to. This is that anonymity point. Obviously not anonymous because I can see them. If one of these was piping over Tor, then I would see the exit node. Right? So if I had like a Tor only transport, then I probably would just get, oh, that worked. Yeah, if I had a Tor only transport, then I would just see one exit node for all of them, or like one node.
How do you discover your peers?
Aha, so this is what the routing system is for. And the routing layer in IPFS includes a DHT and includes some other, so we'll have some other routing systems. For now, it's just a DHT. And for now, it's Kademlia. Although here, because we're in the same network, we also have local DNS. So you can actually discover each other here without the DHT. And the bootstrap nodes for the DHT are here. So if you do IPFS bootstrap, these are the bootstrap nodes. You'll see that all of them start with QMSOL because that's SolarNet. We call it SolarNet because they're all planets. This is Jupiter, Neptune, Pluto, Venus, Saturn. Pluto's a planet, guys. Sorry, Neil. Uranus, Earth, Mercury. It's like, what? E? E's not a planet.
Connecting up IPFS nodes without?
Yeah, so I could actually like, yeah, so I could, great question, let's try it. I'm gonna kill a daemon. Die. Right now it's, oh, it's, the API is open. If I think I close this, should I soon? Anyway, I'll kill it. So now, if I remove, so I can do bootstrap -- help to figure out what to do. It has bootstrap remove. So I can do rm -- help, and it says an option in bootstrap rm is to do -all and remove all bootstrap peers. So, oh, removed all of those. No more. So that means that, by the way, you can do bootstrap add to add some of those. Let me, so then we can do bootstrap IPFS daemon, and this would launch the thing. If I do that. So now it's connected, and that was really fast because it didn't have to bootstrap both of them. I wonder if it's connected to anybody else. It's got one peer, and that's, I think, locally. No, it's not. Yeah, it is locally. 10.3.17, 10.3.17, 129, and 107. So I'm connected to somebody. So yeah, I found somebody. No bootstrap peers. I believe that I should be, if that person is connected to the rest of the network, I should be able to still, so I could ask, I haven't shown the global gateways yet, so I wonder if this will work, but I should be able to take this and go, so if I go to the global gateways, this is a set of public nodes that we run with the gateway at port 80. And this will just take any requests that you have and pipe it through IPFS. It's like a last mile resort, that if you have a link that you want to put into the HTTP world that people want to use and look at, they can look at it through the global gateway. And right now it says gateway dot, but this will go away and it'll just be IPFS.io. We hope to someday get a TLD and then really do like just /IPFS. But I think what's going to happen before that is that we'll make extensions. And what might even happen is that this gets implemented in browsers, which would be sweet. But for now, it's gateway. And if we do that, I think that's a cache somewhere. That was really fast. It was way too fast. So that means that that file got the gateway, searched in the network, and maybe it had it in its local cache and pulled it out. But let's try adding something here. So IPFS, so echo hello from the Meetup. Somebody add me randomness. Somebody say something. 12? 12. And more numbers. Going to possibly come up with that. Maybe it was a blend. And so hopefully this will work. I'm not sure because this is like not bootstrapped to the gateways. Like this would be pretty impressive if it worked because let me see, do I even have public addresses? Yeah, I don't know if I have public addresses. This may not work. Public addresses means like that it has like punched a hole through the NAT and it's able to be dialed. Right now our hole punching is not amazing yet, so sometimes it fails.
How would it go? Are you learning addresses from the other people you're connected to?
Yes.
Or are you only learning those from the initial bootstrap?
I am learning addresses through the routing system. So in the routing system, I say, hey, who has, so the routing system is to answer 2 questions. One is, 3 questions. One is, who has some object? And then I get a set of peers. Then I take those peers and say, where is this peer? And then I get back a list of addresses. And there's a whole bunch of complexity into this problem in terms of like recency and maybe that person moved to a different network and all sorts of amazing, wonderful peer. This is what peer-to-peer is hard. Like multi-transport and multi-addresses and moving around in the network, it's just not built for it. The internet was not built for peer-to-peer directly as we're doing it today because NAT and middle boxes and all that kind of stuff. So we have to do all this work around it, but we do that work and it answers that and we should be able to resolve this maybe. I might have to bootstrap.
So you removed all of your bootstrap nodes. The only way for the gateway to have seen you is that you got an outside node from the peer you connected to in the local net.
So I already have, I'm already connected to some, so somebody found me. I'm connected to a whole bunch of peers now. So I did IPFS farm peers and I have a whole bunch of other ones. It means, because the DHT will periodically like bootstrap itself. So there's like proper IPFS bootstrap, which is just get to the network. And then the DHT itself has its own routine for bootstrap, which means that it will ask the routing table for other random peers, and it'll like add it to its own routing table. So right now, I got a whole bunch of other people because the node was asking for them. So this should be able to resolve. So let's find out. It's not resolving.
How long will it wait?
There's a large timeout. That's annoying. Did I add it right?
What's in the solar hash?
That's there. What's that?
What's in the solar?
Oh, there we go. Oh, I got it. Yes. Oh.
That's really impressive.
You got it. That was really slow. That was like terrible performance. But yeah.
What's the status on real-time communication uses?
So like piping live chat, like live video chat.
Yeah, WebRTC.
So we're not fully there yet. So we will. It's become clear, and a lot of people have told us this. It's become clear that we need to have some sort of pub sub in it, where people can like subscribe to feeds of changes. So that'll come in at some point. It's not fully there yet, but hey, look, it added stuff. And let me show you the video. So I promised that. So let's do this file that I was going to show you. That over here. Let me open a new terminal window. I should paste. Sometimes my computer decides that copy paste is not a function that it wants to do, and it's annoying. So this is just an HTML page. So this is like some hash/play. It's an HTML page, and what is it doing? It's like creating element, video, audio, track, pulling in some lib, video.js.css, looking at a hash, looking at render. It's taking window.location.hash.substring1. So if everybody knows JavaScript and the DOM model will know, or like the HTML module, that it'll look at the current URL of the page, look at the hash and everything beyond that, and where is that used? That is used in render somewhere. Render, this is complicated. Hash, parens, update. Let's not follow it, it's too complicated. But it calls render, and in here, it creates a video. So if we were to go to this page on its own, we'll see nothing. Once we be like, oh, video player, but the title says video player, but there's nothing in there. But if we instead add pound this other thing, so what is that thing? Let's look at it. So, sorry, let me do the 25%. If we do less. So right now it's stuck somewhere. There we go. So it has a poster, video.mp4.webm. So let's try adding it. And I'll do it yeah, so let's try and run it. So what this is doing, I have to do it twice. There we go. This is video piped through IPFS through this video player, and it's pulling it from the network. We can seek, and so now it like. There we go.
So this is the actual download speed. It wasn't cached.
What's that?
Was this cached before, or
this was not cached locally, no.
How does it download similar to BitTorrent, where it downloads in chunks for different nodes?
Yes. Okay. Yeah. That's a whole bit swap thing that I explained.
Okay.
Yeah.
Can we get that video on our laptops right now, or at least that picture of the tree?
Yes. So you will remark upon the difficulty of. But wait, there's more. Call today, and you'll find that we do have a mapping from DNS to IPFS, and something in between that's faster. So I might go a little bit into IPNS, which is a way that you do mutable references, so that you could have a reference and so on, and we can talk about it. And maybe I can demo it, but faster than that might be to just give you this link through some channel.
Maybe a comment on Meetup.
Like this Google URL shortener. So try that now and see if it works. Can you see that? Capital B ZPT753. By the way, this is a very interesting point. So what we just did here is we had some hard to describe resource because it's cryptographic and hashes and so on. And we asked another service to give us a name to it. This implies that named systems exist and that some names are better, some more readable or better at something than others, right? In IPNS, we decided to separate the two functions of a name, which is, one is give you a mutable reference that you can update, and two, which I can hear, and two, I know that sounds so well now, and two is the second function of a name is to be human readable, right? Can we all agree on that? Two functions of a name, mutable and human readable? Well, maybe we should call it the IP pointer system instead of name system, because IPNS is not human readable on its own. It gives you a hash of a public key, which is by definition not readable. But what it does is that if you have, I can go in and explain it. Yeah, sure. Let's just explain it now. So far, we've seen IPFS URLs. Let me see if I have a slide for it. I'll just do it in paper. It's better. This looks cool. No, that's not a hash. This is a hash. So I have this object, right? Like readme or something. That's probably not going to work because that video doesn't have a link called readme. I have this object, and I want it, every single time I change it, like as somebody pointed out, I'm going to be creating more stuff. So what about immutable references? Sorry, mutable references that I can update. This is where IPNS, for name system, comes in. And if you take, this is what SFS does, that I described before, where you can hand people the hash of your public key, and they can use that as a reference. So I can take IPFS ID, and I can take the hash of my public key, and I can do that. So in fact, I'm going to just show you that example. So let's echo more randomness. Anyone? Pluto. Hungry. Pluto hungry into IPFS add. So I get, whoa. There we go. And we then do, so let's verify that it's there. It's there. So, you can do /IPFS if you want it. Whoa, 9E. I'll do it even with, let's do it even with a directory. So make their var. That's the var. IPFS ls on this, and we have this directory. We can do /foo. Ls won't have anything. Cat. All right, so far so good. We have a directory with a file called foo inside of it that has Pluto Hungry, right? So we should be able to resolve that in our local gateway. Let's go localhost /IPFS. So Pluto Hungry. If we go to the directory, we should see the index and so on. Now we should be able to go to gateway.ipfs.io and look at that. If it resolves sometime soon. Sometimes with NATs or like different gateways will have like different, every single time that you hit the gateway, you hit a different one. So come on, resolve. This is too slow. I didn't restart the gateways today, so we have a memory leak somewhere. And they might be slogged down by a bunch of people. Let me do that.
Videos, for instance.
What's that?
A bunch of people downloading videos, for instance.
Right. Oh, there we go. It resolved. No, that was the local one. Never mind. Hasn't resolved. So git protocol infrastructure make cake. No, cake will do all sorts of other stuff. Let's see the Ansible. Bootstrapper deploy. I'm going to reboot them because that will make them go faster. We have this like horrible memory leak somewhere in one of the libraries, so we have to like reboot things every once in a while. And it will knock off everyone who's like piping stuff to them right now. Ha! Oh no, authentication failed. I think one of them just closed. Some of them are going. There we go. No. Ooh, didn't resolve.
Okay, Juan, why don't, if there's anything, just kind of final words.
Yeah, sorry, I could be going for hours on this. So people seem interested, so I wanted to like answer the questions. But yeah, I can stop at any moment. So I also want to be mindful of people's time. So
yeah, so I think that you'll be here for more. If people have questions, you're going to be here to answer questions. I just want to give people a chance to.
Yeah. So how about this? If you want to go now and don't feel obligated. Actually, here, who wants me to keep going? And then I can keep going for those people. So a few of you, is it okay with the place if we stay a little bit longer?
Yeah, I think so. I just want to, sometimes it's fun to network as well and chat. But please keep going here as well for a while longer. That's fine.
I can, okay. Let's have a time limit, and that way 20 more minutes.
Sure.
Sound good? All right. What IPNS allows you to do, it resolved at some point, so it resolved in some of those. That was really slow, but it did it. If we go to this, it'll have a thing. So we can, so the way that the name system works is that this hash of my public key, I can bind it to any other hash or path in the system. So I can say, I'm going to bind this name, which is IPNS / the hash of my public key, to this other hash. Not this one, actually, to this one over here. So, foo, right? So I'm going to do a thing called IPFS name publish. And I'm going to publish this hash. So what that's doing is that it's taking that hash, creating a record, and signing it with my private key, and then pushing it to the DHT. So it's talking to a whole bunch of nodes in the DHT and storing that record in there. And for some reason, it's like taking a while.
And how is it deciding which ones to store on?
It's based on, it's content addressed. The DHT is content addressed there, so the hash of the public key, so it bases it on the hash of the public key and stores it there. So when people that have my public key, or have the hash of my public key, can go and ask those guys for the last record.
But, say that one more time. Let's say I have, a few terabytes that I push. Who's that going to?
So on the record, so you only have to update the record at the very top.
Oh, it's the record that you're publishing.
Yeah, think of it like DNS. Think of it like DNS.
All right. Sorry. For some reason, I was being stupid.
No, this is like a bunch of random. So publish name to QMBQAP something. So that means that I can go now to the hash of my public key. So again, this thing, and if I resolve it locally, not in /IPFS, but let's go to localhost first, /IPNS /that, I should get a directory. Check that out. So it resolved the directory and then use that as the latest version. This is the way that Git handles help. So think of IPNS as a branch in Git, or a tab. So when you update it, you push it again. So you just write on top of it, and last writer wins.
So what if two people have your private key, they push...
Two people have your private key? So you have a shared key, sure.
You have a shared key.
Yeah.
And someone in China also publishes some name.
Yeah, so if you decide to take on the work of saying, we're going to have multiple people writing to the same key at once, you can come up with a way of resolving conflicts. The way you want to do it is you actually are storing records and your resolver should look at all the records and have some function for picking between the records. That happens to be a pluggable thing that you can define in the record itself. So that is a very good question, and it's a very long explanation, and probably don't want to go into it too much, but you will be able to define a validity on the record that will tell the resolvers of the record which one to pick.
And it's up to the writer, not the reader.
What's that?
And it's up to the writer, not the reader.
It's up to the writer and the reader to agree upon what that function will be, which there will be some basic ones like TTLs or timestamps or a Git chain, or like a chain, take all ancestor, or take one between a block between, blockchain time, you can say like, pick between block 100 and 105 or something. It's valid between that time. And look, it's resolving the name. So that's how that works. Cool, yeah.
Can you make published names permanent?
Can you make published names? So the published name is permanent in a different way. The reference is permanent, but the content isn't permanent, right?
How is the reference permanent?
Because when I give you the hash of my public key, like you can resolve that any single time, right? There's these two-sided things. One is the content gets permanent references that are permanently tied to the content, and the other is I'm giving you my public key and the hash, and that's going to stay that way. And I'm going to publish records that are going to update it, and you have to resolve that. So the name system, intrinsically with a name system, you have to be able to resolve the name. A name is a way of establishing a common way to agree upon the value of something, and we're just saying that resolution has to go through the routing system, in our case. The DHT.
So the DHT never deletes anything?
The DHT right now, no, it does delete things. So the name will expire over time. So if you want to keep it there, you keep republishing. The same way that DHTs work today. But different routing systems will work differently. So you could have a different routing system that's just like a huge append-only log, like a blockchain. You could write through the blockchain. So you could turn Namecoin into something like this, like trivially, right? Yeah?
When you were asking for randomness, I said money tree, and you heard hungry.
Oh.
So can you show us how we would update the same reference?
Oh, yeah. So with money tree. So, all right, let's do that. So now I echo Pluto. Oh, sorry, guys. Money tree. So actually, I wanna echo it into some directory bar. Where did I put that? Is that somewhere else? Opti. Yeah, echo. So IPFS add -r bar. So let's just verify that this works. Localhost 8880. It's there. Foo 25 bytes. Money tree. All right. So now we take this hash and say IPFS name publish that hash, which is the directory. It'll take a bit. This publishing, but think of it like a different DNS, right? Like a much faster DNS, where this is like resolving in seconds, publishing and resolving in seconds. This is really slow. Like I want to get this down to below a second, so that you should be able to publish and resolve a name under a second. We're not there yet, but we're gonna get there. There's just optimizations in between here. So now I can go back to. So all right. So this is the same URL, right? So I should be able to enter and Pluto money tree.
Okay.
Yeah.
That's good. So can you explain, because I missed somewhere in there, how are those two things with their different content addresses linked into the same thing?
Because this is IPNS, which is that the name system. So that means that wish I could like draw. I wish like Brett Victor's Brett Victor's seeing spaces were around, so I could like just draw DHT in air and like you could see it. But imagine a big DHT with a ring, right? And a whole bunch of computers are tied to this ring. And I publish to some set of people in this ring at the content addressed location of my public key. And I store records on there. So I'm publishing to the same location.
So you're storing to a path in the namespace of your public key /food within the namespace.
Yeah, so I'm just updating the pointer. I'm just changing a pointer. I can create an arbitrary namespace in there. I can create directories. I can do anything I want.
You just have like one mutable slot per node?
You have one mutable slot per key. So if you IPFS name publish.
The only thing you put in there is a directory reference?
No, you can put anything you want. So IPFS help will tell you that the name defaults to the name that you're publishing to defaults to your local ID, but you can generate more keys into it. So right now we haven't fully implemented that. We're speccing it out right now actually, and you'll be able to publish to other names. So you'll be able to share names, and you can publish anything you want. So commit history would be the best thing to publish because then you can see the versions in the past.
So if I want to publish thousands of things in huge trees, I just publish the top of that whole tree directories, and every time I change it, I just republish that top hash.
Yes, exactly. So imagine that like the Bitcoin or the Ethereum blockchain become names in a namespace, and you could go to the public key, like to Vitalik's public key, and like resolve that every single time. And he had like one machine that just kept updating the record to like point to the new head all the time. Right? And so you won't get perfect consistency over time. Like it'll be like dependent on the routing system. But DHTs can get to 1 second resolution times. Other name systems like other routing systems like and local DNS would be milliseconds, and it varies by routing system. But it's important to decompose this because that gives you the flexibility to choose a different routing system for it. And you will have nodes that will be able to speak multiple routing systems. Like that's totally kosher. Totally good. Yep.
Question / hack off. Let's fast forward to a time when web applications can mutate objects in IPNS. So you can have a web page where you can actually fill a form and say click save and something consistent happens, which is not reality right now. But let's fast forward to that moment.
Yes.
Okay, what does that mean for the fact that web security is origin based?
You mean the web origin stuff? So thankfully we have a thing called subpage origin that is a standard the browsers are implementing today, and it's spec'd out. I don't think it's fully finalized. It may be that other browser vendors decide to change it, but people have already recognized the fact that the domain name system is not the only notion of scoping, and that maybe you want to be able to scope based on path. And so subpage origins means that browsers, that if you set a header on the HTTP request that defines a different origin, then like you can have subpaths that have different origins.
Okay, so then IPNS paths, for example, are namespace to the...
And today, what we can do today is have a gateway that resolves subdomains. So if you fetch like subdomain hash dot whatever, it'll give you that same stuff. So
How is the pointer updated?
Through the DHT, like what I was describing. So you have the DHT and you're pushing stuff onto the DHT, and people can resolve it from the DHT. So it's dependent on the routing system, as I was describing.
My understanding of DHTs is that you give it an address and it gives you a file corresponding to that address.
It's just a key value store. So a DHT is just a key value store. It stores hashes and values, or keys and values. And so the key in this case, so the word key here is overloaded. The key of the key value store of the DHT will be the hash of the public key. So we're putting that as a key. And the value is the record. And so treat of it like a black box database. You're putting the hash of the public key and a record. And when I want to publish again, hash the public key and new record, and keep adding.
Okay, so in other words, it's DHT implementation dependent.
Yes, exactly. So it's routing system dependent. Yep. Yep.
Yeah, so I'm going a little bit far away from some of our technical stuff here. I'm just thinking, of some really cool applications. So, the blockchain. Blockchains are one good one. If you, let's say you're a company that has a bunch of computers with some storage, but no servers, and you want to make it completely centralized. You gave some applications earlier about you know, Egypt cutting off the network.
Yep.
Okay, I guess I have some examples. My next question was, you know, this is an Ethereum meetup, so the Ethereum guys, I think they've talked with you a couple times.
Yep.
So, I mean, we already have this example of putting the blockchain on IPFS.
Yeah, so last time I chatted with both of them, with Vitalik and Gavin, we discussed the capabilities of IPFS today in being able to like robustly serve like Merkle trees directly, like the Ethereum Merkle tree on this. And IPFS is suited for that because it is meant to be a Merkle DAG transport, so it is precisely for that. So it seems like a really good place to collaborate. I think we have been extremely busy with getting to our alpha and releasing that, and the attention that came from that, and pushing it. And I think also the Ethereum core team has been like really pushing to develop on their side. I know that several people over there are playing with IPFS already and using it for different stuff. There is a lot of potential for like some sort of merging of efforts here that would be really cool to see. It might happen soon, it might happen later. At the very least, if we both link into different things, we can overlay one on top of the other. Like we could use Ethereum transports in IPFS directly and be able to resolve everything directly. We could use we could put a full IPFS node inside some Ethereum clients and store stuff directly to IPFS to make it any other IPFS node access it. And there could be like more actual buy-in and tie-in where you could have an Ethereum node be defined as including an IPFS node inside of it. I think it's probably a safe idea for Ethereum to black box that and say this is the interface, and then IPFS could match that interface. But if I was designing Ethereum, I wouldn't depend on any other infrastructure without an interface there. That's how I would do it. I mean, we don't plan on going away, so everybody could depend on us, but just interfaces are good, right? Interfaces are good, and I think like it makes sense. I think there's a lot of possibilities with making sure that the namings and the formats are all the same, so that the links stay the same, and that could be really cool to do. So, and we're if you notice, we're namespacing everything, right? So like all our hashes have /IPFS, /IPNS. So the goal is to allow you to, you know, IPFS mount here, which should have my node running. Oh, Fuse is terrible.
I guess what I was trying to do was I mean, are there some specific things that Ethereum does that IPFS doesn't? I mean, you talk about these public keys. So one thing that you can imagine a blockchain for is sharing public keys.
Yep.
But I guess
I mean, there's a lot of these systems are so big that there's a lot of shared like sets of things that we both do. But I think, as far as I understand, the goals of Ethereum is to construct a consensus building process that can run smart contracts anywhere. And like that's something that IPFS doesn't do. You could build it on IPFS, but it's something that IPFS doesn't do out of the box.
Right. So I guess one other thing I was thinking about, you talked about this, you know, getting the reputation of the, let's see, nodes that are trustworthy. I was just thinking about whether that could benefit from interacting with Ethereum. Like, you know, develop if you had a reputation system for IPFS nodes.
I mean, that could be one of the ways that you route, maybe through social network instead of a gauge team.
Yes, so I think that's probably like one really great way to collaborate, where Ethereum contracts can use IPFS links and references and resolve them into it, and even store themselves. So Ethereum agents and contracts the code for them could be stored inside of IPFS. Yes, exactly. It is exactly right. I want to show you this one example of booting off of a VM, which is really cool. So in this VM directory, I have a makefile, and I'll make it clean. And I will make, which means that it'll tell VirtualBox, oh, I have to mount. Sorry. Let's mount. There we go. So /ls. There we go. So, all right. So, by the way, if you see here, by the way, I've mounted the file system, so I can go into it and ls in there and open things as I would. What's that? It should tell you not to. One choice that we've also figured out is that we'll have /IPFS/local, and in there will be the references that you have here, like in the local node. But yeah, /IPFS should never list the whole thing. And /IPNS, for example, I can go into /local. /local. Should I CD into it? Yeah. Does this work? All right. Don't remember how. There's a way to. I can touch. So echo to here, and that should be republishing. So open. Is that automatically republishing? Yes, it should be. It should be. Whether it is another question entirely. Survey says not close, but not cigar. Oh, is that? No, that's not my public key. This is my public key. Come on. No. Am I like copy pasting the wrong thing? Oh yes, you're right. So what is my public key? It's this. Haha. Yes. Sweet. All right. It works. I'm just stupid. The code is better than me.
So to clarify, what you basically did is you just, I mean, it's still IPFS, you just mounted it so that everything you do just kind of auto-publishes.
Yeah, ooh, it broke. I blame Fuse. I blame our use of Fuse. Yeah, but that's the goal. That's the idea. Maybe it doesn't do append. Okay, now refresh. No, that's the wrong one. Localhost. No, we need some like, there we go. IPNS. Ooh, that's bigger. Yeah, so that works. So append for some reason is broken, so that's a bug. But I can write more stuff, save it, and refresh. Should be able to. It's there. Refresh. There we go. It's there. The VM that I want to show you. That swarm peers. I have a whole bunch of peers, and I say make. And what this is going to do, it's going to provision a VirtualBox VM and boot it from the network. And now I have a VM that's booted from the network, and I can run it. Run. And you see how fast that was? That was awesome. I'm actually cheating a little bit. There's a node close by that has some subset of the objects, but we can get it that fast within a data center.
So I didn't follow that whole thing. Can you sum up what just happened?
Oh, what just happened was that I have a makefile in here that we can distribute with IPFS. In fact, if we get on a Getter channel, do you have VirtualBox installed? Does anybody?
Maybe.
This would be awesome. So this makefile. IPFS add. The makefile will do it. The makefile will do it for you. Take this path, and now we can be able to resolve localhost 8080/IPFS/that. Should be a makefile. Google URL shorten it, which we'll need. We'll have some sort of thing for this. And now you should be able to go to that URL, which will give you that makefile. And you can take that makefile, put it in your machine, and then type make, and it will boot up the VM. At least it should.
And it's pulling the VM down
from IPFS, yeah. And it'll be really fast because I'm here.
Yeah.
So if our computers find each other, then it'll be good.
And if you do it before you fall off the network, you'll have
Yes, and then
It'll be slow.
exactly right.
This relies on the mount being active.
The makefile does rely on mount. Oh yeah, that's right. You have to IPFS daemon and then mount because it uses the local file system. What we're gonna do is we're gonna take Docker and we're gonna look at the storage engine and swap it out with like a resolver through IPFS, and then just boot Docker containers directly from IPFS, and it's gonna be awesome. We don't have that today. Sorry. We've been working on it, but it's not really there yet.
Do you know about Sandstorm?
Yes, I really like Sandstorm.
Sounds like that would plug in really nicely.
Yes. I once I was hanging out with Kenton at a party, and I was like, Kenton, I have this crazy file system idea. You should totally use Sandstorm with it. And he's like, dude, every single person I know has a file system idea. I don't want to listen to another one. Fine.
That's good.
So I was like, fine, I will wait, and then in a year, I will talk to you again. So it's close to a year. We'll go talk to him again, and now we have something to show for it. And it's fine. Like, we just have to build it first. So now we can use it.
Just have to build it first.
Yes. All right.
Alrighty, guys.
I think
burning questions. Anybody? Please.
I'll show you the parting gift, or the parting thing to note will be this amazing video editor that my friends Matthias and Max have been building. It's called Playback. And if you go to playback.github, no, I think it's like, let's go to Playback and see what happens. No, that's not gonna work. So if you go to this webpage, you see the Playback open source JavaScript video player. So this is a really cool video player that's kind of like VLC, but it, not kind of like VLC, it doesn't even do like 1% of what VLC does, but it is very simple, and its whole goal is to make it as easy to watch media as you can. So I have it installed locally, and what it can do is that I can take an IPFS object like this one, so this Sintel, if anybody's seen Sintel, so I can go playback : / and then an IPFS path. I believe it should work with just this. I think that works, and I should be able to click it. Oh my god, come on. So I should be able to click it, and this opened Playback, and now it should be playing.
It's fine.
It's playing. It's Intel. And if we go, it'll seek. I already had some of this cached here. Some of it isn't, so we might find like a place where it isn't cached. There we go. That takes us a bit. Cool. So that's the state of affairs with how fast we can deliver to content media players like Playback. And this works with VLC too, but it has to pipe through the gateway. We implement it natively into Playback. All right, cool. Any last questions or anything?
Please, hopefully it's a quick one.
Can you talk about the organization behind the community around IPFS? Like, who are you guys?
That's a really good point. So a while back, I had this idea for this crazy thing, and I said, great, I'm going to go build it. So then I started building it, and I considered, it was so compelling that I just dropped everything and started working on it. And I was deciding what to do, and I looked at the future and I said, what will I want to be doing in the future? And I realized that what's really important to do, or at least what I think is really important to do, is make sure that the internet keeps evolving over time. And there are certain ways in which it's evolving that I'm not happy with, and there are certain ways in which it's evolving that I want to make sure continue to happen, and some other ways that we want to introduce. We want to be able to make it, like I want to end up with a lab, a research, an R&D, protocols and tools, research and development lab for the internet, where we would make things like this, where we could make things like Git and BitTorrent and Bitcoin, Ethereum, and all of these kinds of ideas could just say, great, let's go and build it in there and make it. And we would look at the network stack and say, that's broken, let's go fix it. And that's what I dream of. And that's what Bell Labs and SRI and Park and generally the IETF and the IEEE were like all doing for a long time and still do. But I want something that I think is better than what's currently out there, and Bell Labs doesn't exist anymore. So I want it, and I decided that I was going to build it. And so I started a company called Protocol Labs, Inc. And our goal is to create this kind of organization in the long term. And so we'll be building a whole bunch of protocols that are all, some of which will have services alongside, some of which will have tools, some of which will have cryptocurrencies involved. So also ours is Filecoin. You might not have seen it yet, but because we've been pretty silent about it recently. But Filecoin is also ours, which is a data storage network and electronic currency based on Bitcoin. There's other stuff that we'll introduce around this because we need to be sustainable and independent. And so I decided to build a company. It's going. We're building this whole stuff. We are very open source, so we do everything with people that want it to exist for themselves. We're building this because we want it to exist, so other people want to build it because they want it to exist. We have a huge community. So, and we've been very careful to differentiate Protocol the company from like IPFS the community, and like basically Protocol the company is like a few of us, and like we're really more like the IPFS community right now than Protocol the company. But I am not letting go of that because that's like a critical piece that I see is like, I want to live in a world where I could say, this is broken, let's fix it, and we build the tool, and we deploy it, and it's there. And to do that, we need resources, and we need to build a company and a business behind that. So that's what the protocol's about, and for now, we're building IPFS and a whole bunch of other stuff.
Right. And what do you need? Like, you need coders?
We need hackers. So we need, really, at this point, if you know Go or JavaScript and are like peer-to-peer systems and like this kind of stuff, come chat with us. We are pretty open with working with all sorts of people. We're distributed. There are some of us in different places, and we work very openly with a whole bunch of other people that are not part of the company or anything. We do a whole bunch of contracting, so if you are tied up because you don't want to work, you don't want to join us full time, or you can't, many times people can't because of a variety of reasons we do contracting. We're very flexible, but ideally, we want to work towards full time after we know each other and we get to we decide that oh great, this is a great person we want to bring on. We can hire from full time and part time. But we just need more people to help build. At this point, it's just we have all these ideas. It's all very raw to some extent. You saw. It'll get better. It's already pretty good. You can use it, but it just needs to get better over time. About less than a year ago. So about a year ago, there was no code. Less than a year ago, there was code, a little bit, and then Jeremy Johnson, who's the second employee of Protocol Labs, joined, and he and I have been hacking for a long time, and I'm with some other people. So a whole bunch of people have actually contributed at this point, a lot, and my thanks and everybody's thanks to them for making this possible. But we've been hacking away and making all of what you see today, and more that you will see soon, more that you haven't seen that we have, and we just need more people. So, cool. Thanks.
Okay, so you'll be around here for a bit?
Yeah.
Okay, let's thank Juan.
Thank you very much. So kind of everyone, and Chris for organizing this and putting this together and having us here. Okay. So thank you very much. This has been really, really great.
All right, you bet.